Hello. Hello, good evening. Uh, am I audible?
Yes, ma'am.
Thank you. Thank you for confirming, Bhuvneshwar. Okay, so I have shared my screen. Today we'll be discussing the previous assignment questions. So I would try to solve them in detail. However, I understand that these are only my solutions. So this is how I tried to attempt them. If you have any doubts or if you think that the approach is wrong, please let me know. Okay, so the first problem was for a mode propagating in region 1 N1. So they have given defined a nine regions, and the mode is said to be propagating in region 1, and it has a refractive index N1. What is the solution along x direction in region 3 with a refractive index of N3? So we have to tell the solution. So not the exact solution, but the expression for a solution along the x direction in region 3. So the x direction is this way. So the vertical direction is x direction, and n1 is greater than n3, so that's why the mode is propagating in region 1. So if you look at the vertical direction in region 3, there is no boundary for x going to infinity. So so the kind of solution that we expect in region 3 is always decaying solution. So if I have an oscillating solution, then it will keep oscillating to x goes to infinity, and then that will mean that my energy is going to infinity, which is not feasible, right? So if my mode is propagating in the region 1, so in region 1 we will expect a oscillating solution. However, uh, as we go to region 3, we expect a decaying electric field. This we can also think uh, in terms of thinking it as a planar waveguide. So uh, so along the x direction, there is no confinement here. Um, yeah. So along the x direction, if this is my x direction, if I'm plotting it like this, then there is a boundary here. So this that corresponds to this boundary, and a boundary here. But along the x direction, there is no boundary. So so sorry. So there is this boundary along the x direction. If I am considering this as region 1, then this is region 3. I can have oscillating solution till here, but after this it has to decay because there is no boundary for x goes to infinity. So then if I want a decaying solution, then how my solution will look like? So there will be an amplitude term, and uh, and then I expect an exponential decay. So that will be like e power minus gamma x. X because it will decay with the x coordinate. So minus gamma x. And gamma is the decay constant. So we don't have to actually tell what is the solution. We just have to tell the form of the solution. So a and gamma will be the coefficients. One is the amplitude, one is the decay constant. Similarly, in problem 2, again mode is propagating in the region 1. So they are now asking that in region 3 we have to predict the solution along the y direction. So if we just observe, now the boundaries are this and this. So and along y direction, whatever is the solution in the region 1 should be the same as in the region 3, because along the y direction there is no boundary. So the boundaries are along the x direction if we are considering the solution to be along y direction. So so naturally in region 1, since we have a mode, so that will mean that there is a oscillating solution in region 1. So that will mean that there is again an oscillating solution, the same oscillating solution will be there in region 3 as well. So the amplitude might be different, but yeah. No, actually amplitude will also be the same. So yeah, amplitude will also be the same. So that is the approximation here again. Now this time we are approximating a slab waveguide, but the boundaries are like this. Okay. So again, if B is my amplitude, the oscillating solution should look like B. into, say I'm writing it in terms of cos. You can also write it in terms of sine, but the options were in terms of cos. So then, cos of propagation constant times y, right? Because now it's along the y, so my solution will look some oscillating solution which varies with the y coordinate. So there will be a ky into y. So it varies with the y coordinate and with a propagation constant ky, plus a phase term. So if I write it in terms of sine, this phase term will be different. That's it. So this is the answer. Okay. So you can just go through Professor's boundary value problem lectures. In that, he has discussed these things in great detail. Okay. So the third problem, we have to calculate the normalized frequency. So normalized frequency is nothing but the V number. So we have done this multiple times even in the previous lectures. Okay, so calculate the normalized frequency for a waveguide of 0.5 micrometer height and 1 micrometer width, operating at a wavelength of, okay. So they have given us a waveguide. Height is 0.5 micrometers and the width is 1 micron. Right? And wavelength is again given to be 1 micron. The refractive index of the core is 1.5, and of the cladding, which is surrounding, is 1.45. So yeah, so the core is higher refractive index than the cladding as expected. So we have to tell how many, not how many modes, we just have to tell the normalized frequency. So yeah. So after knowing all this, the normalized frequency is just V equal to 2 pi over lambda times A times root of n core square minus n clad square. So we know all the values. Now only question here is, should I take this A? Hello? Okay. Should I take the A to be my width or to be the height? So uh, so uh, so it is known that for the V number we should always take the value of A to be the dimension that is the smallest. So if the width is small, you should take width. If the height is small, we should take height. So in this case, the height is smaller, so we will take that. So I'll get 2 pi over lambda is 1 micron, so 10 power minus 6. A is 0.5 micrometers, it is 0.5 into 10 power minus 6 into root of 1.5 square minus 1.45 square. So now it is straightforward. You will get 0.5 is just 1 by 2, pi times 0.384. That comes out to be 1.2066. Yeah. So from this, one more thing that we can infer is, the number of modes in the waveguide is approximately equal to the V number divided by pi. So from this we see that the approximate number of modes will be 0. So it's more close to 0 than 1. So we can say that this waveguide might not have any mode that propagates along the waveguide. Yeah, but anyways, they had only asked us for the V number, so this is the number. Okay, right. So in the classes we had learned like 2-3 different approaches um, to designing waveguides, and one of the approaches was the perturbation approach. So in the perturbation approach, um, we assume that uh, uh, the refractive index profile is a little bit complicated. We use it only in such situations when the refractive index profile is complicated, and we know the solutions for some simpler refractive index, say n naught, and then I find so I write my equations in terms of this n naught, and then I give it a slight perturbation of delta n to match my original solutions. So so then this the equation that I write with this modified refractive index, they are called modified index modified wave equations. So in the perturbation approach, we use index modified wave equations that have infinite modes, finite number of guided modes, both of them or none of the above. So, in general, such solutions can have infinite number of modes. So this is definitely true. However, we try to approximate the refractive index profile to such refractive index profiles that have only finite number of guided modes, because if the guided modes are also infinite, then it becomes very cumbersome to calculate. So so this is also true, so therefore we say both of them. Okay, so is that clear? So so we have some complicated refractive index profiles. Say my refractive index is low in this region, higher in this region, but it's not very regular, but again low in this region. Then I might approximate it to something like this, plus some slight delta and perturbation. For such a nice geometry, I will have finite number of guided modes and infinite number of other than guided, so non-guided modes. But the solutions to this geometry I already know. So it's good that if I use such a refractive index profile. So um, and then the slight perturbations I can achieve by doing something like summation over the different modes. So yeah, so that is a different thing, but yeah, so we try to model it using a refractive index profile that has finite guided modes and infinite unguided modes. So both of them is correct answer. Okay, calculate delta beta square for k naught equal to 1, n square equal to so much, psi m equal to, okay, so this is also related to the perturbation approach. So yeah, if you just know the delta beta square equation, you should be able to do it, regardless of if you know how to get the equation. So the delta beta square equation is given by, I just write it down first, k naught square surface integral. So surface integral means x integral and y integral. X goes from 0 to 1, y goes from 0 to 1, n square x comma y minus n naught square into psi m, sorry, square ds. So first we will just substitute these values and get the answer, then we will discuss how we got this equation in the first place. Okay, uh, yeah, so now they have given us n square x comma y to be n naught square plus x, right, and then n naught square minus n naught square will go, so we'll only be left with this plus x term. So this will become y equal to 0 to 1, x equal to 0 to 1, x e power minus 2i. So I'm just substituting all the things that they've already given to us. 3x plus 4y dx dy upon again double integral e power minus 2y, same integral values, 3x plus 4y dx dy. Since the limits are same and we are integrating on the same surface, um, I believe we can just combine the two, and then once we have combined, these two terms are the same, so they can get cancelled. So we are left with x dx dy. So x goes from 0 to 1 and y goes from 0 to 1. So then finally we will have x square by 2, that is equal to 1 by 2. Yes, Bhuvneshwari.
On numerator, we have x multiplied by the exponential number. And the different, the integral variables are x and y. So how can you cancel the numerator and denominator?
I was so since the surface is the same over which we are integrating, and the integral limits are also the same, I think we can do this.
But x is the variable of integration that's also involved. That's why I got confused and I got a different answer in terms of I everywhere it is coming now. That's why I got it wrong. I was not able to get the finite value as it was given in the range.
Oh,
So I
yeah.
used
Actually, even
that
when I did it the
integration by
first time,
parts
no? When I did it the first time, even I thought that it is not
method.
possible to cancel like this. But when I saw the answer,
Okay.
yeah. So I
Okay.
don't know
Okay.
means if it's allowed or not. So I'm not that good. But if you're
Yes.
getting some,
Mathematically, we
huh?
cannot do. I think.
Uh, so I'm. So can I write it like x y x e power minus 2y 3x plus blah, 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 upon e power, no, right? You're saying
Yeah,
it.
if that we have to take it into consideration and integration by parts we have to apply now. Even in
Yeah,
the
I tried
denominator
that,
also.
but I'm then
Uh,
we will get a lot of. I tried that in mathematics
yeah,
actually.
yeah,
Then we are
yeah.
getting
That comes in
complex, some
item.
complex number upon some complex number, right?
Yes, 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 ma'am.
Yeah, even I was getting that, but then when I saw the answer,
Yes.
probably they have done it like this. I'm
Okay,
not
but
sure if this
you
is
just
allowed.
mention and forward this one, these kind of
Sure, sure.
problems. Already there was, yeah, in assignment one also there was one question I also mailed you. I hope you
The
recognized
Kai one,
that
no? Yeah, I
real
have
part.
told this to
Yeah, real part.
professor. Yes, yes. But
Yes.
I don't know. Like I don't have access to change anything. Okay. So
Okay.
whatever has to be done, I think professor only has to do it. Let's see.
But
Like
you
by
must
the
just mention it.
yeah, yeah.
Yes, because we have taken this as my coursework. I am doing my PhD. So
Okay.
this coursework this grade will count into. That's why.
Oh, okay. So you guys have a final exam, right? So these assignments also count in your
Yes,
grades?
yes. Yeah, assignment marks out of 25 they will take.
Oh,
Anyhow, it is best 8 out of 12 only.
okay.
Even then.
Yeah, even then. I understand.
Okay.
Right. I will ask professor for a formal solution for this problem.
Yes. Yes, ma'am.
Yes.
Thank you,
Okay.
ma'am.
Thank you. Okay. So the next question, for an embedded waveguide. Yeah. For an embedded waveguide of dimension 5 micrometer into 10 micrometer, having core and cladding refractive index of 3 and 2 respectively, find n effective using effective index method. Okay. So wavelength they have given, lambda is pi micrometers. So if they have given the lambda, we can find out k naught. K naught will be 2 pi over lambda times, okay, not times, so only 2 pi over lambda. I will get it to be 2 into 10 power 6. Okay. kx they have given root 11 into 10 power 6 meter inverse. Everything is meter inverse. Ky they have given to be 3 into 10 power 6 meter inverse. Okay, so we have to find the n effective. Okay, so my n in this region is 3. This I think is 10 micrometers. This is 5 micrometers. And here around is n equal to 2 lad. So whenever we have to use effective index method, basically we are changing the confinement in 2 dimensions to a confinement in a single dimension. So the effective index here is 2, here is also 2. Here we have to find out how much is the effective index. So for finding that out, we basically do n effective is nothing but beta x or beta that I would have got had I been propagating along. So I have not defined the x and y directions, right? So this is the x direction, this is the y direction. So yeah, um, so assuming that I'll leave it. I'll just directly take the formula. Explanation is difficult. So an effective I can find out using the formula. So this term basically I call it as beta x, but I don't know if professor has also called it beta x in the class. So we'll just take it as a formula to avoid confusion. So k naught was 2 into 10 power 6 times n is 3. So 10 power 6 square, 10 power 6 square, I'll just take it out as 10 power 6 first, upon 2 into 10 power 6 into root of, so um, 2 times 3, sorry, 2 times refractive index was 3, 2 times 3 is 6, 6 6 are 36 minus kx square will be 11, so that will become 36 minus 11 is 25, root is 5, 5 by 2, that is 2.5. This one is fine, right?
Yes, ma'am.
Okay. Using the value of n effective obtained in equation 6, the propagation coefficient is. So yeah. So propagation coefficient will be beta equal to root of k naught square n effective square minus ky. So this n effective already includes for kx, so we should not do another minus kx here. So that will just do it twice. So now the answer will be root of k naught square and effective square is 36 into 10 power 6, right outside, minus ky is 3, 3 is a 9, so minus 9, 16, 4 into 10 power 6. The similar thing we could have even got without going to the n effective part by just writing it as k naught square n square, that is 3 square, minus kx square minus ky square. So both will give the same answer. Just that because they said we have to use an effective, so we should use this method. In the lecture, we studied waveguide parameters using an example with silicon and silicon germanium waveguide. Using the same approach, calculate the effect of a 10% reduction in the silicon germanium refractive index on the gamma y value. Based on the value obtained compared to the lecture example, choose the best suited statement. Okay, so I'll just draw the geometry first. So there is silicon as a substrate, then silicon germanium waveguide, and then again it is loaded with silicon at the top. And this is 16 micrometers. This is 3 microns. This is 4.1 micron, 4.1, and this is 6.5. Okay, so yeah, and the axis they have defined it as x is this, y is this. Okay, and the other things that they have given is in the lecture lambda equal to 1.32 micrometers. Silicon refractive index is 3.5. Silicon germanium refractive index they have given it as um, do you have the value? I actually lost it.
I'm on the way, ma'am. I'm just observing.
Okay, I'll check. Yeah, I found it. 3.50125. This is 3.50125. So 10% reduction would mean uh, so they've asked us for 10% reduction. So this is okay, this problem I am not sure of the solution. Just let me know if you think it is wrong. Okay. um, so 10% reduction will mean that I am new and silicon germanium will become 3.151125. So I just did 3.50125 minus 0.35, etc. So now my silicon germanium refractive index is actually smaller than the silicon refractive index, right? So that would mean that um, my mode is more likely to be confined in the silicon because there is air above. Hello. So yeah, so after 10% reduction, I have gotten a silicon germanium refractive index to be 3.15, 1125. Huh. So this number is smaller than my silicon refractive index. So that means that my that is more likely to guide light compared to silicon germanium, because the refractive index of silicon germanium is lower than silicon. So that is what our intuition tells us. So based on that, if I just try to do the effective indexes, then in the center I will have silicon as my guiding substrate, above is air, and below is silicon germanium, and on the sides there is only air here, right? So that was how I approached the problem. So for the center portion, so for the center portion I can write the characteristic equation. uh, so I wrote all that in the MATLAB code, and finally I got my effective index somewhere around uh, so I got the kappa value to be around 4721 centimeter inverse, and I based on that beta I got a 16,000, sorry, 1,66,530 centimeter inverse, and an effective I got it somewhere around 3.4986. So so yeah, so effective index in the center region I got it around 3.5, slightly less. In the air region, so we can just say that the effective index is 1 on both sides. So now I can use the symmetric waveguide characteristic equation, and based on that I can get my gamma value. So yeah, here the H will be 16 micrometers, because now so first we reduced it to the uh, to 3 refractive index along the y-axis. Now since after we have found the effective index, we have to use uh, basically for finding the effective index I use 3 micrometers as the confinement. So now after finding the effective index I have to use 16 micrometers in the characteristic equation. Y by k by, so I am assuming it as TE mode. Then from that, again by putting this in the MATLAB code, and also with this we have to put the gamma y equation also, k naught square, and let me just label this as n2 and this as n1. So this will be n2 square minus n1 square minus kappa y square. So solving this equation, LHS and RHS, and we can find the values of kappa y. And for the fundamental mode, the kappa y will come out to be 1950 centimeter inverse. Sorry. And the gamma wave will, like, at least it came for me as 159570. So this is way greater than the gamma y that we had got in case of silicon germanium refractive index as 3.5 something something. So in the class we had got the gamma y to be 2352 centimeter inverse. So this high gamma y can be attributed to the fact that now the light is not guided in the silicon germanium region, however it got guided in the silicon region, and the cladding is silicon germanium on one side, air on the others, all other three sides. So the field decay rate along the y direction increases. So the decay rate has increased. So you see the decay rate has increased because of stronger confinement, because of 10% reduction in silicon germanium refractive index. Is this how you also did it, or you were getting some other answers?
The first option only I also typed based on understanding only. I didn't work out this up to this level and all
Huh. Yeah, based on
because that
understanding we can
refractive.
guess it, right? Hmm.
Yes, yes, yes.
Yeah, that is also fine actually.
Huh?
Huh.
Yeah. Will you be uploading this recording tomorrow, ma'am?
Yes, sure, I'll
Why?
upload
Because
it.
I'm on the way. I didn't know
Sorry. Yeah, okay, it's
down
okay.
this
Yeah,
workout of this September.
yeah, I
Yes,
understand. Okay, yeah, I'll upload the recording.
yes, yes. Thank you.
9th problem. The normalized frequency parameter is given by V equal to k naught a root of n11 plus n22. N1 square plus n2 square, where a represents the dimension of the waveguide. So we already discussed this. Considering a channel waveguide of width 1000 nanometer and height 500 nanometer, the cutoff condition is determined by using an appropriate value of a. In this particular case, a value has to be the smaller number. So the smaller dimension here is the 500 nanometer. That is height. So height is the correct answer. Last question. In a symmetric slab waveguide, neither fundamental TE nor fundamental TM mode has cutoff. The statement is true or false. So the statement is true. So if we just look at the characteristic equation, LHS and RHS um, of the symmetric slab waveguide, um, we see that the RHS is a function that looks somewhat like this, and this goes to infinity at kappa equal to 0, and there will be some kappa max here, and then tan functions will always go like this, right? So so for whatever value of kappa max, even if kappa max is very small, these two curves will always cut each other at some point. So yeah, you can just try plotting the RHS and LHS for different values, and you can check that the statement is actually true. Okay, thank you.
Ma'am, one request, ma'am.
Yes, yes.
Can you solve some model problems for the upcoming assignment, ma'am?
Uh, okay. Today I cannot, but I think I can upload it over the weekend. Will that be fine?
Yes, ma'am. Yes.
Yeah, sure.
And one more also in
Before Sunday,
forum,
I'll try to upload.
yes, ma'am. In forum also, yeah, I some doubts in the lecture also. If it posted in the forum, nothing, no, there is no response at all. Can you forward this to
To Shankar
wherever
sir,
it
huh?
has to be mentioned?
Okay.
Yes, not whoever has to respond, they have to look at.
There is some issue on the technical side. The other TA is not getting any of the mails that or the forum announcements. Okay, I'll forward it to
Okay,
her.
ma'am.
I don't know. Or I
Yes,
can do
ma'am.
one thing. I will discuss them in the video that I upload. Okay. So I didn't check
Yes,
the
ma'am.
forum actually.
Okay.
Okay. Thank you. I'll try to
Okay,
upload
ma'am.
before
Thank you,
Sunday.
ma'am.
This lecture I'll upload now only,
Yes.
but the extra discussions I'll upload before
Yes,
Sunday.
ma'am.
Yeah. Thank you.
Thank you, ma'am.